these days, the OEMs aren't producing 350,000 individual vehicles, of one type, like a F-150 or a Silverado. It's a lot less, but they're more highly customized. So those are kind of the industry drivers that we're seeing out there. I'm going to, through probably the rest of this discussion, just focus on the electric, connected, and autonomous, and how systems can play a role in. So, I mentioned the industry is moving very quickly, from mechanical components to mechatronics components to now experiences. It was not too long ago, if you all remember the GM spinoff Delphi, they were a mechanical parts company and they produced, components for vehicles. I saw some data that stated that they're now producing more lines of code than they are physical parts. So quite a shift going from a parts manufacturer to a high-tech company. So with this shift in the industry, what's the impact on the suppliers? And I'm thinking many of you out there are suppliers to the industry. This is the market size we've seen in specific parts of the vehicle in 2018. And this is the estimate what it's going to look like in 2025, which is just 4 short years away. So a huge growth in electric drivetrains, batteries, electronics, and a pretty sharp decline in things like transmission, brakes, and axles. So you can see as the industry is changing, the impact on the suppliers will change also. I was reading an interesting article last week about a supplier that you're probably all familiar with named Mali, German company that has produced a lot of mechanical components in the powertrain area. They've just recently come up with a brand new brushless electric motor that they think will really make great gains in electric vehicles, much longer life cycle, longer durability. So you can see how some of these companies kind of make the transition from kind of old parts and systems to the new. So what are some of the enablers that are allowing the industry to do this? First is early validation. Virtual models, replacing physical models. It's much easier, quicker, cheaper to create a virtual model, build it and break it than a physical model. You can get instantaneous results, answers, and your costs are a lot lower because you're not using physical materials for the testing. Another is breaking down the silos between your organizations, between engineering and manufacturing, between sales and engineering, understanding all your cost regulation standards, having those in separate silos, kind of unifying into what we call the digital thread, and we'll touch on that a little later. Finally, trace and reuse. To be able to take parts code, anything you used in the past, and reuse it, and understand the traceability of those parts throughout your system, subsystem. So the strategies that we're seeing is kind of this whole thought of digital continuity from early design through validation, through product and end use. To not model components, model individual systems, link those systems together. Once I have those systems linked together, to validate them virtually. And finally, for some customers, take those validations and have their customers experience it in virtual use. So we talked a bit about the industry and what's going on. I'm going to take a little step back and talk specifically on systems engineering. The term systems engineering was actually developed by Bell Labs in the late 1940s when they began building communications network. Interesting experiment I did when I was given the task of kind of mobilizing GM for model-based systems engineering is kind of walked down the halls of the vehicle engineering center, and I ran into 15, 20 people I knew, and I asked each of them, what is systems engineering? And of those 15 to 20 people that I asked, I think I probably got 12 different answers. So right now, back then and right now, the term systems engineering means a lot of things to a lot of different people. So there is an organization out there called INCOSE, the International Council on Systems Engineering, and they are to systems what SAE is to the automotive industry. So I went to INCOSE and I pulled down their definition of systems engineering. And again, you probably already read this while I was talking, but I've got one word highlighted there. That's transdisciplinary or multidiscipline. So we're talking today about systems kind of in the terms of electronics, software, but you can build a completely mechanical system or electromechanical system. So systems engineering is used for more than just electronics and software. So I just want to get that point across. Secondly, adding virtual models to these is part of model-based systems engineering. Right? To not do systems in hardware, but to virtualize them, do analysis, verification, validation activities to make sure that those systems meet their required need. So that's the modeling portion of this. I will put in a little plug. INCOSE is a great organization. About 10 years ago, I started the Automotive Working Group within INCOSE, and it's still in use today. So for those, INCOSE also has a lot of training and educational materials. So if you're at all interested, please go to the website, kind of peruse what they have, and if you want to join, you can then access all of this great automotive information from the Automotive Group. So systems engineering has always been described kind of as what we call the systems B, where we take initial upstream ideas, concepts, requirements that a supplier may get from an OEM, and create this architecture, detailed hardware, software that meets those requirements. Then crawling up the other side of the V, verify the components, systems and subsystems. So this is the systems engineering V is something that you'll see quite frequently. And it does provide end-to-end system traceability all the way from requirements to validation, which is why it's such a powerful concept. So adding modeling capabilities just enhances that by enabling what we call a digital twin and the ability to run multiple tests, multiple validation much more quickly and with much lower cost. So many of you have probably been doing systems engineering for quite some time. You might not even have known it. When we look in those tools and environments that are used out there, you'll recognize a lot of these things. Perhaps the biggest tool that we use in this environment is Excel. I think Excel is the most widely used, and I'll even call it a modeling tool used on the planet. We all use it in our working lives and even in our daily lives sometimes. But you'll see all these other tools out there. SysML is huge, as well as as many of these others. But as you can see here in my graphic, they're all kind of islands. Take information from system A to system B can be sometimes problematic. It's almost like trying to combine two different languages, like French and English, or Chinese and Japanese to English. You lose sometimes things in the translation. So, the goal in this is to move to what we call the digital thread, right? To take those requirements, integrate them with the functional analysis, which is what you use to describe how that system's going to work, the logical architecture, the things that you'll put together, right, to make that function work, and finally the physical design. Put these things in one single digital thread to eliminate those translations or eliminate those islands between data. There's a lot of add-ons that go to the digital thread. I mentioned earlier that you can do a chassis, fully mechanical in a model-based systems engineering methodology. To do that, you have to have a lot of physics. So there are existing behavior and simulation models from Modelica that can be plugged in there to really enhance, right, how you would do a chassis system. So that was just one example of traceability and the concept we call RFLP, which is the integration of requirements, function, logical, and physical design. So systems engineering, I think, is a much more open platform than something like CAD, for example. There's a lot of parts, right, from a lot of different disciplines that are coming together. In the industry is out there adopting standards that the software partners like Dassault Systems are using to do R&D and to provide solutions for their customers. So several industry groups out there that are driving these standards are, I mentioned in COSI earlier. There's a organization called the Global Automotive Advisory Group, which is also headed by people from many of the OEMs that are working together to build standards in this specific area, and obviously other industry players like ProStat. So they're driving standards for openness. There's also connectors out there that are being used to bring data from many different areas together, like RecIF, OSLC, and you can see some of the things like AP 233, AutoZar. Some of these should be familiar, but a lot of work being done out there to provide openness, right, to bring the software, electronics, electrical, and mechanical systems together. So my goal was to make this kind of short and sweet. So hopefully I've done that. So I guess to conclude, provide the agility that the industry is seeing and will continue to see a need. The ability to model your systems and validate them virtually is key. Also, the ability to bring multi-disciplines together, your software developers, hardware developers, you may be buying chips from a supplier, right, to bring all that data together and synchronize it and eliminate those islands of automation is also very important. And last but not least, the ability to trace and reuse, capitalize on assets that you've already made is a great cost and time saver. So a model-based systems engineering methodology and mindset will help you do that. Dassault offers some great tools that will also allow you to achieve it. So with that, I'm going to turn it over to Sanjay.
Hi, next we're going to invite Sanjay Khurana. Sanjay works for the technology software engineering manufacturing company, Dassault Systèmes. And Sanjay is a previous colleague and a friend, but more importantly, he's an expert in requirements engineering and model-based system engineering. Sanjay's been working with multiple industries, conducting in-depth research into customer business processes, support critical engineering business transformation strategies using engineering fundamentals. He's simultaneously working with industry and academia to advance the state of the art, bringing new model and simulation technologies together. Sanjay's the Director of Technical Sales for Cyber Electrical Fluid Systems at Dassault Systems. He holds a bachelor degree in industrial engineering and a master's in engineering. He's also a certified systems engineering professional from Incosi. So with that, I'd like to introduce Sanjay. Thank you.
Thanks, Mike. Can you hear me okay?
You sound good, thanks.
And are you able to see my screen as well? Okay, great. All right, thanks, Mike LaLande, for the great introduction here in terms of the need for systems engineering for the automotive industry. So what I'm going to do here is talk a little bit about what is Dassault Systems doing with respect to providing an end-to-end systems engineering, model-based systems engineering solution on the platform, and what is the thought process behind it. So with that, what you see on your screen is a portfolio of systems engineering that we have with respect to, sorry, there was a question. If you could please mute yourself if you're not talking, I'd appreciate it. Thank you. So what you see on your screen, Mike was earlier presenting how systems engineering is represented on a system engineering wheel. So what you see here is throughout the entire process of system engineering, when you see on the left-hand side where the requirements and the overall decomposition takes place, and on the right-hand side of the wheel where most of the integration, verification, and validation takes place, we have applications on our platform that provide capability at each level of the system development. So going through all the different abstractions, we provide modeling capabilities at the early level from a 0D perspective, going into 1D, 2D, 3D, and ultimately into manufacturing for 4D. So essentially, the platform that we have for model-based system engineering brings together the different abstraction levels, and when we interpret that in terms of modeling and simulation, as I said, going from 0D all the way to 4D, we have the modeling and simulation level of capability at every level of abstraction. Okay, so in terms of having this entire sorry about that. I'm back. So what you see here is when we talk about systems engineering, one of the ways when we look at system engineering is how to manage the complexity. As Mike was talking about how the product complexity has increased over the last few decades in terms of how complex the systems have become. So when we look at how we approach it from a systems thinking, systems engineering perspective, the idea is to approach the systems development in the form of abstracted layers. And what you see on your screen is the framework that we have at Dassault Systems, where we take the systems first from a system of systems approach, where we are trying to model what exactly is the contracting authority or the acquirer of this system is looking for. So developing an architecture which is more at the capability level, which includes not only the system, the mission of the system, but also the enabling environment, the enabling systems who are going to either impact or going to be impacted by this system. So that's at the level of systems. Then we go into developing the global system architecture of the actual system that needs to be developed. And of course, there is a multi-physics part of it, and then there's the controller part of it. And then as you can see, as we go down, we peel the onion, we keep going down into these abstracted levels. We have the 3D as well as the electronic and software aspect of it, where we're talking about making sure that we are going through these abstracted layers all the way from system of system level to the detail level with hardware, software, mechanical components. The idea is to have it done on one single platform is to make sure that there's a digital thread that is available or is going to be built as you go through these different layers of abstraction from a modeling perspective as well as a simulation perspective, and the stakeholders who are actually involved in developing those artifacts. So the idea is to have a digital thread go through these different layers of abstraction, top down, and then parallelly going horizontally through the different variants or the different alternates that are going to be managed as part of the trade studies that are going to take place during the system development. So that's the intent behind doing it on the platform. Now, when we say we do it on a platform, bringing together all these different stakeholders and modeling and simulation artifacts from 0D to 4D, we are not talking about pushing only the Dassault Systems capabilities and applications on top of our platform. Our platform is very open, as Mike was earlier talking about. We have capabilities where you can actually plug in any modeling or simulation capability at any of those abstraction levels, whether those are third-party softwares or in-house development softwares. We are able to still introspect the models that are developed in external applications, and then build the digital thread between those artifacts as well as the artifacts that are developed natively on the Dassault Systems platform. So taking a step further, system of systems engineering, we, as part of our No Magic acquisition that took place 3 years ago, we have integrated a lot of framework and capabilities that are made available by No Magic into our 3D Experience platform. So at a system of system engineering level, we support multiple frameworks. What is represented here in front of you is the unified architecture framework. So there are multiple frameworks that are available out there, supported by different industries and organizations. So we are able to develop we are able to provide the development of system in context of any of those frameworks. With respect to multiple different industries, we support for defense industry, for example, the DODAF or the MODAF or the UPDM kind of framework. But in general, the unified architecture framework is what is available across multiple industries. It's industry agnostic and is leveraged heavily in terms of system development. So what it provides is, as you can see, when you are working in this framework, I have a video playing on the left-hand side. We are at the system of system level development. What you see on your screen on the left-hand side is our SysML environment, where at the mission level, you are doing some modeling. And the whole intent here is to say, when you are going through that V model at every level of abstraction, so at the mission level, even though the system is in a very descriptive mode, we are able to do some early level simulations to identify if the description of the system is matching what the stakeholders are looking for. If it can actually validate some of the needs or requirements that have been stated by the stakeholders. So at every level of abstraction, when we talk about whether it's descriptive modeling, analytical modeling, or any kind of detailed modeling, we have verification and validation capabilities to continuously validate against the needs that have been specified by the stakeholders, to make sure that we don't have any scope creep that is taking place in the system, or we don't have any requirements which are erroneous in nature, which are going to cause quality issues or other integration issues down the line. Just a little bit more to give you insights when we talk about, for example, the unified architecture framework. We are managing different kind of views. We're talking about the service views or operational views, multiple different kind of views that are available as part of that framework. So working within that framework gives you the capability to develop views for different stakeholders in the organization who are involved in the overall system development lifecycle. And those views are actually built from the one authoritative or a single source of truth. So everyone is looking at the real-time data in terms of pulling the context that they are trying to pull in with respect to the role that they have defined on that authoritative source of truth. All right, so moving on from systems of system engineering to more system level engineering, and this is where we are leveraging the SysML language. Again, Mike touched on this a little bit. We have the full SysML language integrated into our 3D Experience platform to do the system level definition. Just an insight into the SysML language, we're talking about four main categories here in terms of structure, behavior, requirements, parametrics, which is supported by 9 different diagrams. So this is typically those diagrams that are developed as part of the system development. And those diagrams, when we actually you know, store them on our platform, those are living and breathing diagrams. Those are not just static pictures. Every object that is defined on that diagram in terms of a block or a port or an interface is recognized by the database as a specific object, and we are able to establish traceability between those objects. And the traceability, we will go from specifically a requirement that is in place, a function that is being developed to address that requirement, a specific port or an interface that is enabling that function, and then so forth, going into any software functions or any hardware functions. So the traceability, as I mentioned earlier, goes throughout the different levels of abstractions, connecting those modeling and simulation artifacts at an object level, not just at a document or at a model to model level, but at the object level, making sure there is full requirement allocation and traceability, both top to down and bottom to up. All right, so moving a little bit more into the framework, Mike also mentioned INCOSE. So we strictly go by the INCOSE System Engineering Handbook. It's literally the Bible that we have in terms of the development of the overall model-based system engineering approach on top of the 3D Experience platform. So we inherit the entire system engineering lifecycle as per the ISO 15288. We actually take all the technical processes and technical support processes, and those are laid out in the 3D Experience platform to support the end-to-end system development lifecycle. Now, when you look at the system architecture, one of the expectation from the system architecture is to provide an overarching effect to the entire system development, right from requirements to the trade space analysis to the discipline specific architecture and the detailed design development. What you see here on your screen is the system model being the heart of the system development. There is an expectation that there is bidirectional traceability between all the different artifacts that are actually developed as part of the system development lifecycle. What we often see is that if you don't have a strategy in place to consume or connect what has been developed in the system model to the rest of your enterprise, if you're not putting a strategy in place on how that system architecture is going to be more consumable by the rest of the enterprise, typically the model-based system engineering strategy will fail and will not provide the kind of return on investment that you're looking for. This is an issue that has been faced by multiple organizations across industries where they have adopted very strong system architecture capabilities. I call it a problem of 20 to a 2000, where you have 20 system engineers working in this great tool set, developing great system architectures. But if there is not a strategy in place on how that system architecture is going to actually be used to drive electrical systems architecture or a fluidic systems architecture or software architecture, how that system model is going to transform into a 2D schematic model or a dynamic behavior model or or a 2D fluidic model and so forth. If there is no strategy in place to either connect and navigate through this information for the rest of the enterprise, or to be able to take this information and transform them into the lower models, lower abstraction models, then that the overall model-based system engineering strategy will fail. So what you see here on your screen is we are talking about traceability, one, systems architecture, and the traceability with requirements, the different frameworks, the detailed design, the trade space analysis. We want to make sure that the traceability exists, again, at every level of abstraction. The trades are done at the early level, at the descriptive level, where we are supporting that with the 0D modeling, at the behavior or the equation level, where this is where we are supporting with our 1D models, or the detailed design where we are supporting with 2D or 3D models. So at every level of abstraction, there are simulation, verification, and validation capabilities available, which further help you to do all the trades that are necessary to go through the decision making that needs to happen at every level of the system development lifecycle. Now let's talk a little bit about the framework that we have in the 3D Experience platform. So we talked about the industry standard frameworks that we follow in terms of the Unified Architecture Framework or many others that I named earlier. Besides that, what we have is this kind of a hand-holding pattern and hand-holding framework within our platform. If you are not using a certain framework, or you're using framework only at the system level, at the system level, we have what we call as the cyber magic grid. Those of you who are familiar with the No Magic company before they were acquired by Dassault Systems, there was a magic grid that existed without the integration of the detailed design into that overall magic grid. So with the acquisition of No Magic at Dassault Systems, we have extended that magic grid to include the detailed design phase and or the implementation phase, as you see it on your screen. And this is where we renamed the entire grid to be the cyber magic grid. And as you can see, the key thing to note here is that we have the problem state analysis, we have the solution analysis, and then we have the implementation. Something to note here, which is very important, is that we have requirements going throughout the entire process of system development. Sometimes there is a wrong notion that when we talk about RFLP, requirements, functional, logical, physical, as part of the system development lifecycle, it gives a notion that requirements come first, and then comes the functional and the logical, and then the physical design. Well, it's not really the case in actual systems engineering. Requirements are something that continue to evolve throughout the entire process. As you do the problem analysis, you are capturing the needs that the stakeholder has, or you're converting them to system requirements depending on that problem state analysis. And then as you go through the solution, we talked about the different artifacts that you build in support of building that solution, the 0D, 1D, 2D, 3D models. Now, those same models are consumed at the problem level, and then later on, those models help you build a solution. And those models, as you are building the solution, as you go through those different abstracted layers of modeling, they actually help you refine those requirements. So the requirements, when we talk about in the 3D Experience platform, is not only requirements management, it's a continuous process of requirements development that is managed throughout the entire system development lifecycle, going all the way into the detailed design and then all the way to manufacturing as well. The key thing to note here is that, of course, the system of system engineering and system engineering that we have the links, the traceability does not only exist at the system level, but it starts from the system of system level. So the needs and the capability architecture that is defined at the system of system level continues that traceability into the system level. And then, of course, going across is also the specialty engineering. So any of the abilities that are defined, any of the security or safety requirements that are defined are again taken into consideration throughout the entire system development lifecycle. I wanted to touch a little bit more on requirements because requirements are at the core of the model-based system engineering strategy that we have at Dassault Systems. Um, we have gone through many different industries and many different organizations, where we have analyzed how systems engineering, or whether implicitly or explicitly, how it is deployed. One of the things that we have observed is that the requirement errors is a huge issue, and especially in the T&M industry, also the transportation and mobility industry, the requirements is a huge issue because there are requirements which are, up to 70%. I'm not saying everyone has that issue all the way up to 70%, but up to 70% requirements have errors in them. And so there are, those errors, they actually manifest themselves into all kinds of issues when you are integrating, verifying, or validating your system, or you're launching your system, going through any acceptability testing, or launching your system into the market. And needless for me to say that, it's much cheaper to address those requirement errors as they are in the development phase. As they get baked into the system level functionality, the cost to fix those errors can be exponential. And of course, if the system is launched and has to be recalled, it is a dent on the reputation of the organization. Plus, the costs are, the costs that you have to deal with are further. There are more lawsuits and other things that get added to the costs that you have to deal with. So adding a little bit more color on requirements, I wanted to make sure that I drive this message as part of the platform strategy. We're not only doing requirements management, but requirements management is just one aspect of our requirements engineering strategy. We do requirements planning where we can, as part of an overall project or a program plan, we can lay out more like a system engineering development plan, or as part of the system engineering management plan, which is typically referred to as SEMP. We can have a requirements development plan. So typically, to manage the requirements throughout the all the phases of system requirements, or the preliminary design requirements, or the critical design, or any of the reviews that are managed throughout the entire process, we have a complete planning process that is fully integrated into the platform and traceable. So basically, what we are bringing is traceability between your design artifacts and your program and project artifacts. So it's very key to keep that in mind, that we are driving that traceability not only from a design perspective, but program and project perspective, so that the program managers have full visibility into how the system development is coming along, all the way down to the granularity of how a system, a specific interface in a function that has been assigned to a stakeholder, how that is being matured, and when that interface is going to be developed, and so forth. The typical requirements development phase, we have tools where we are managing the elicitation of the needs. So specifically, if you are working on a wide field project, you're gathering the requirements from a multitude of stakeholders spread across the globe. How are you going to elicit those requirements or those needs, and how are you going to manage them as you sift through all the needs, taking out the duplicates and the needs that are in conflict with one stakeholder to the other? The entire process is available. We have the analysis phase where you are actually doing some requirements in loop kind of simulation. In these early simulations on functional requirements provide you the capability to simulate your requirements against the other requirements. the requirements are actually supported by a code. So every time you are writing this requirement, it is written based on a library of conditions. So instead of a dumb textual statement, it is actually supported by if, then, and, or, shall be not kind of conditions. When you write that statement, requirement statement, it generates a piece of code in the background, and that helps you simulate those requirements against a function, against a piece of code, against other requirements. So again, the idea is to start validating as early as possible to eliminate as much errors as possible. So without even getting into some of the modeling stages, we have the capability to simulate the requirements. Then we have the specification, verification, validation. This is where we're talking about all the different modelings, the capabilities available at different levels of abstraction, and the verification and validation criteria available throughout the entire process. Requirements management, as I said, is an integral part of the system development process. So not only are we actually providing the tools to develop these requirements, but at every step of the way, as those requirements are developed, they are captured by the requirements management capability. One of the other things to keep in mind is that when I talk about the different abstracted levels of 0D, 1D, 2D, 3D, and all the way to 4D, not everyone is expected to use all the different abstracted levels. Depending on what role you have, if you are a system engineer, you probably stay in the realm of 0D to 1D modeling. If you are more of a discipline specific design engineer, if you're an electrical designer, let's say, you will be staying in the realm of 2D schematics, developing the net diagrams or the wiring diagrams. And then if you're a 3D designer, you're more on, let's say, developing the harness, the 3D harness, and then so forth for a manufacturing foam board. So what I'm saying is that depending on the role that you have and at what level of abstraction you are engaged in the system development, you will be leveraging those modeling and simulation capabilities as part of your engagement on the 3D Experience platform. Requirements traceability, again, the traceability is a key aspect. The traceability is making sure those requirements are allocated, and then those requirements are verified and validated throughout the entire process, enabled by the simulation that is available on those modeling capabilities throughout the entire process. This is more of a detailed view of the CyberMagic grid that I was talking about. So again, as you can see, we guide the user through identifying, understanding the problem space, building the use cases, building the context diagrams, where we understand a system that needs to be developed, but we don't know what that system is going to be. At this level, we are capturing the interaction between the system and the stakeholders to build an overall context diagram. Now, the parameters is another key aspect of our 3D Experience platform. So when we talk about parameters, we're talking about effectiveness, suitability, performance parameters. So for example, here at the level of system, we're typically talking about the effectiveness of the system, where the acquirer of the system, or even it's within your organization, your marketing or product launch organization, they are laying out, how is this system going to be effective? How is this system going to be suitable for the stakeholders or the eventual users of the system? So you're laying out all those conditions are being laid out and captured as part of those parameters. The beauty of working on 3D Experience platform is those parameters are not captured as part of a document or requirement statements. Those parameters are captured as attributes in the database. So there is traceability at the parameter level in terms of which parameter needs to be satisfied, which effectiveness parameter is going to be satisfied by which performance parameter, and which performance parameter is going to be satisfied by which key performance indicator or key performance parameter. So all of that is defined, and there's traceability at the parameter level, where at a high level, what is being defined is that the system the weight of the system cannot exceed a certain number of pounds. And then as you go through building the system, you are looking at first all the critical subsystems of that system, and then you're doing a weight roll up, and then you're going further down into the component level design, and then you're doing the weight roll up. Or in terms of performance, whether it's engine speed or in terms of the performance for 0 to 60 in 3 seconds, 4 seconds, whatever it is, there are effectiveness performance criteria that are defined upfront that drive the entire development of the system. Because every time a stakeholder at those different levels of abstraction is trying to make a design decision, it is ultimately driven by the constraints or the criteria that has been put in place based on the effectiveness, acceptability criteria, or multiple other abilities that can be defined at that level of definition. Okay, I just quickly wanted to show you a video, and then I will conclude. I thought it would be nice to show a little bit about traceability, because this is the key aspect of our platform when we're talking about integrating multiple different modeling and simulation capabilities in our platform. So you see this, the earlier snapshot on your screen was in the Cyber Magic Grid framework. As we organize those artifacts, each one of these diagrams are live diagrams that are navigatable. You can zoom in, zoom out. You can select any of these objects and go through the traceability aspect of it. So what you're looking on your screen is a context diagram right now. This is enabled by the No Magic integration in our platform. So I will skip this a little bit forward just to, as you can see here, we're talking about the different functions. You can see the navigation. You can see the navigation into these diagrams that are defined leveraging the SysML language. Okay, so what you see, I've been talking about some traceability. On the left-hand side of your screen, you see the traceability. This is where we are able to keep the traceability between the requirements, the needs and the requirements, and the functions, the architecture that comes about as part of the development of the system. Those allocations can be managed. You can see it's a simple drag and drop of one object on top of the other, or there are patterns that you can write with the business rules that you have to automatically connect based on the different keywords and other criteria, how a particular model will connect to another model or another set of requirements. So those kind of things can be done in terms of maintaining this digital thread. And once the digital thread is created at any given point of time, you can do impact analysis in terms of a requirement changing. What will be the impact of that requirement that is going to change on the artifacts that have been developed downstream? Or let's say during trade studies, you see that during a simulation, you find out that you are able to either meet or exceed the performance criteria. There can be a change that can be pushed from bottoms up for that requirement to be adjusted. It's a similar pattern where we are able to quickly see what requirements will be impacted by the change, whether it's top down or bottom up. Okay. This is just an entire process here in terms of how the entire system life cycle is managed. So just that yellow racetrack that you see, what we're saying is that we essentially start out with capturing the stakeholder needs. There are multiple applications available to capture those needs and then simulate those needs at an early phase to make sure we take out any duplicates, any requirements that are actually in conflict with each other, and then develop the measures of effectiveness, measures of suitability, which is going to lead the criteria in terms of system development, what other performance criteria, what other testing criteria that needs to be developed. So you can see that we go from stakeholder needs to stakeholder requirements, defining the safety, security requirements, and then going through the system, subsystem requirements, testing and simulation, all the way to software and hardware requirements. And as we go through the development of these artifacts throughout the entire process of system development, traceability, trade studies, and verification validation is something that goes throughout the entire process. So with that, I will wrap it up to say that the platform that we have is very heterogeneous in nature. We are able to take not only the artifacts that are developed at each level of abstraction by only Dassault Systems applications, but by the applications that are provided by other third parties or homegrown applications. We have the capability to enable the entire model-based system engineering process, taking into account those external applications, being able to introspect and build the digital thread at an object level between all those different heterogeneous environments, and making sure that the digital continuity stays throughout all the different abstractions of the system development. So with that, thank you. Mike?
It's
Cannot hear
very
you, Mike.
big. Hello.
There you go.
Sanjay, thank you for that presentation. We all know it's a very big subject matter to try to boil down into a half an hour or so. Good job of doing that. So next, we'd like to introduce Sachin Patil, who's going to show a more in-depth explanation of model-based system engineering with presentation and more of a user role environment and how that might work. So Sachin has 10 years experience in PLM system engineering. He's actually a solution architect for us, and he's also focuses on many of our automotive clients and MBSE's approach in PLM as well as ALM. So with that, I'd like to introduce you to Sachin Patil. Thank you.
Yeah, thank you. So good morning, ladies and gentlemen. Thank you, Michael, LaLande, and Sanjay for this wonderful session on MBSE. And today I will be take you through a topic of advanced mobility architecture definition, which talks about how the MBSE system on 3D experience platform is architected and implemented. So let's quickly go through the agenda. We will be talking about the current MBSE implementations challenges, architecture overview with the 3D experience platform, then enterprise business process mapping, then solution layout for one of the ISCs, which is based on model-based system engineering, which is safe, smart, safe, and connected. And then we will be having our conclusion. So the current MBSE implementation challenges for any organizations are the awareness and the change resistance. The human factor plays a central role, particularly if the key players have different level of MBSE knowledge and adequate time for training is not granted. Consequently, change is not always accepted compared to existing approach, or it creates strong resistance due to lack of expertise to deliver the required artifacts. It is method definition and extension. So it is often necessary to customize an appropriate method according to a defined purpose and scope. It is a challenge to set up the required method, document it, and facilitate it with modeling rules, guidelines, tool customization, and training materials. Further challenges arises when new method extensions are needed. Also, many times the question arises which methodology we should consider here. The conventional methodology, which is like waterfall, which is suitable for the overall vehicle development, or agile methodology, which is mostly used for the software development. Then modularity and reusability. So many organizations still follow an opportunistic and isolated reuse approach where a set of data is copied and pasted from one context to another. Unfortunately, this still happens even with the system models and result in losing the source of truth as soon as the copied source of or pasted target is changed. Complexity management. The evolution of system through the growing numbers of component functions and interaction has dramatically increased their complexity. The issue here is with both the high number of model elements and the dependencies between the whole element and model. Very often, this complexity level takes existing methods and tool to the limit. This makes it difficult to build a complete and consistent system view that integrate multiple engineering discipline. It makes it extremely complex and also costly to model and simulate the behavior of system in the context of complete product. Tool dependencies and integration. Also, the problem are caused by engineers using a multitude of disconnected system engineering tools that can be create thousands of different models of systems being developed, with each tool having its own view or model the system. But these individual models are largely disconnected from each other and they are authored and managed by different legacy and proprietary tools. So company needs to pick a set of tools and train employees accordingly. Such a decision is not an easy task. There is a no tool that satisfies all the needs. Moreover, integration between system modeling tools and other, such as simulation or requirement, is still solved with specific solution. Last but not the least, comply to the new automotive regulations and the safety standards. So it also to the question is how to define the processes across the tool sets and across the different business module, which should be aligned with the automotive regulations and functional safety standards, and how to align all these business processes along with that. So let's take an architecture view. To address these challenges is an integrated model-based system engineering environment that drives the creation and management of artifacts of complete development phase of existing or future system to accurately capture and predict their behavior. So we create a digital thread with the 3D experience open development platform to tie up all the engineering disciplines together to collaborate, define, and share a common consistent architecture definition. This 3D experience architecture addresses the challenges with collaborative and open platform for MBSE. This architecture enables user to design and experience the product and systems through a continuous engineering development. The first layer here, the system architecture definition, context, we can leverage benefit of digital continuity to design a complex products and systems starting from the requirement specification to the early validation, design implementation, and optimize, verify, and validate these systems through a virtual simulation at the conceptual design stage, reducing the need for physical prototypes, which also includes openness for many OSLC tools to integrate with platform to work in collaboration and exchange artifacts accordingly. This layers give flexibility to adopt a different methodology from waterfall and agile methodologies as per the system requirements. Then the data governance layer helps in harnessing a digital workspace that unifies all stakeholders and enables model-based system engineering, is transforming the way new projects are coordinated during the entire development phase, which has unified project management, configuration management, issues, and change management throughout the product lifecycle. Then the last layer is for the native application, which contributes in conventional design, multidisciplinary designs like harness, fluid system design, multi-physics simulations, through which all involved disciplines work together to create a holistic digital model to incorporate the requirements of mechanics, software, hardware, and kinematics. The closed loop digital continuity between design and validation improves engineering productivity and delivers improved productivity, product quality. And the system traceability matrix facilitates the continuity between all these three layers artifacts and help them to collaborate and manage them well. Most importantly, 3D experience gives the flexibility to define the business processes to adopt the automotive standards and functional standards like automotive spice, ISO 26262. So now let's look at the how this business process mapping is done. So from the project planning with detailed project task and work breakdown structure along with the costing, milestones, stakeholders, task allocation, assignments can be managed through the project management in Innovia. So for a new program and project initiative, very first step is to record a requirement feature which need to be introduced or initiated from scratch, which results in detailed requirement specifications, structuration. Many organizations still uses Excel, Word, file formats, or DOS uh, and, for the requirement capturing. The 3D Experience platform gives functionalities to integrate your Microsoft tools or DOS with the platform and perform the complete life cycle management of these requirement artifacts, which further includes the simulate requirements to detect incorrect, missing, conflicting requirements, as mentioned by Sanjay, to validate that specification meet the safety requirement. When we talk about the MBSE adaptation, the most important step is to transformation of the conventional engineering bill of material to MBSE aligned bill of material. So as due to complexities we have now with paradigm shift towards the electrification and the embedded systems in automotive, so it is difficult to manage the component of bill of material as they are not just mechanical, but we have to deal with multidisciplinary data like electrical, software, hardware. To adapt the MBSE approach, we need to transform our traditional engineering bill of material with unified hybrid structure to accommodate CAD, electrical software data model, product tree, metadata, which will help us to improve collaboration and productivity and reduce complexity. So we can now connect the engineering bill of material with these MBSE artifacts as per the requirement specification. We start with the functional architecture definition, which defines the services the product must provide to fulfill the requirements. Functions can be broken down further into the sub-functions. For each functions that the input and output flows are defined. Also, behaviors can be added to functions, this functions and this modeling language of UML or SysML. Then the logical architecture of the product using component relation between components and the behavior. So logical architecture represents an intermediate abstraction between the functional and the physical architecture. So the component of a logical architecture represent abstraction of the physical solution. The component of logical system thus defines functions, properties and interfaces that are common to range of physical design alternatives. So here we also define the electrical and electronic and fluidic topology definitions and the software architect for the logical artifacts. Then we start with the definition of the physical architecture, which is an arrangement of system elements and the physical interfaces which provides the design solution for the product, service or enterprise, and is intended to satisfy logical architecture elements and system requirements. For this detailed design, uh, OEMs and suppliers uses multiple authoring tool sets with like CATIA V5, SolidWorks, Creo, NX. So using the Power by integration capability, now 3D Experience have capability to integrate all the these third party or the other authoring applications with the 3D Experience platform. For the successful MBSE adaptation, it is not just important how to define the model of the system, but also to simulate and validate the models. So we need to follow the V model to verify every architecture from unit level to system of system level, which includes requirement in loop, software in loop, hardware in loop, and model in loop verification methodologies. So 3D Experience platform have capabilities to integrate these simulation and validation processes with the RFLP model definition. Once we define this complete uh, engineering bill of material, so here we can see the traceability matrix, which is used to create a traceability between the all the RFLP artifacts along with the model definition till the validation step. Once we define the engineering bill of material, we go ahead and define the manufacturing bill of material and the service bill of material uh, with the digital continuity approach on Delmia, where we define the manufacturer item definition, process planning, resource equipment allocation, factory layout, and factory simulation on Delmia. So the best part of implementing 3D Experience platform to adopt MBSE approach is to having a unified configuration and change management process, which helps not only to govern the physical design, but also to cover the scope from requirement, functional, logical, till the manufacturing bill of material to service bill of material. As I mentioned, the 3D Experience platform openness, it is not just restricted up to multi-CAD integration, but platform can be integrated with the ERP and MES and supply chain management databases to exchange the data information with the engineering bill of material and manufacturing bill of material whenever needed. And the openness is also extended to integrate with the model-based system tools like DOS, FMI, MATLAB, AutoSAR, Control Build, and many more. So, which makes 3D Experience platform as a unique and powerful platform to adopt MBSE approach. So to demonstrate the 3D Experience platform capability to adopt MBSE approach, we bring you a smart, safe, connected demo, which will describe the mobility system architecture, the system architecture to define missions and services through multiple connected systems, considering all stakeholders and product service life cycles. Requirement engineering and validation, which simulate requirements to detect any error before design and test automatically the system against its specification. Vehicle system architecture, the conceptual architecture definition from requirement to functional and logical subsystems. Performance driven architecture, which is performance assessment orchestration with domain experts. Deliver scalable, reusable, and safe architecture for electronics and software, electronic and electrical, and software architecture. Define and optimize electronic and electrical architecture by distributing functions to hardware and software component. So then vehicle functional safety to identify failure mode and assess gravity effects to build in safe design. So as a conclusion, normally I can close my presentation with a conclusion, but at this moment, there is no conclusion as the journey of MBSE has just started. So as a DI Square, we are looking forward to work together with all of our customers to develop tailor-made methodologies and concepts to adopt MBSE approach for their digital transformation journey. And as Sanjay mentioned, that define a good strategy is the most important factor here. So we request all our customers to please contact us for the detailed demonstration and consulting on MBSE topic with 3D Experience platform. Thank you all for your patience. That's it from my side. Thank you.
So, ladies and gentlemen, if you have any questions in regards to any of the material that you've seen today, please email us either to the contact information that I shared, or you should have received invitations from Michael Ratliff. We'd be happy to answer those questions. But with that, that's the conclusion of the webinar, and we thank you for attending. Have a great day.